everyone. Today we study Calculation 2. Let's study the new knowledge, Taylor and Maclaurin series. Now, please think about the following question. Maybe you ask me how to find a polynomial function Pnx such that f(x) is close to Pnx. Pay attention to the fact where Pnx equals this expression, where f is a function whose n plus 1 derivative exists for each x in an open interval I. Continue the given point A and the remainder Rnx equals fx minus Pnx, which can be estimated. Next, let's study the following definition: the infinite sequence, Taylor series, or Maclaurin series. Firstly, the power series representation of a function in x minus a is called his Taylor series. Furthermore, note the condition: if a equals a special number 0, then the corresponding series is called the Maclaurin series. Let's learn the uniqueness theorem by theorem A. Suppose that f satisfies the following expression for all x in some interval around the given number A, where Cn equals the nth derivative of fx over n factorial. Because the coefficient is unique, then the corresponding theorem also means the expression in x minus a is unique. Then, let's study the Taylor's formula with remainder. Let f be a function whose n plus 1 derivative exists for each x in an open interval I. Continue the given point A. Then, for each x in I, we have the following expression, where the remainder or error Rnx is given by the following formula, and C is some point between x and A. Pay attention to the fact the power is n plus 1. Next, let's study the Taylor's theorem. Let f be a function with derivatives of all orders in some open interval between a minus r and a plus r. The Taylor series, namely the following expression, represents the function f on the open interval between a minus r and a plus r, if and only if the limit of Rnx equals 0 when n tends to positive infinity, where Rnx is the remainder in Taylor's formula and C is some point in the open interval between a minus r and a plus r. Now, let's continue to study the following classical examples. Example 1. Please find the Maclaurin series for sin x and prove that it presents sin x for all x. Now, let's analyze the question. Because fx equals sin x, f0 equals 0. Because f prime x equals cosine x, f prime 0 equals 1. Similarly, since the fourth derivative of fx is sin x, its value at 0 is 0. Thus, the Maclaurin series is the following expression. Note the variable x can take any value So, the domain is the real number system, namely minus infinity to positive infinity. Then, proof light for all x, we have the limit of Rnx equals 0 because the absolute value of the n plus 1th derivative of f equals the absolute value of cosine x, or the absolute value of the n plus 1th derivative of f equals the absolute value of sine x. We have the absolute value of Rnx is less than or equal to the absolute value of x to the power n plus 1 over n plus 1 factorial. For all x, the limit of x to the power n over n factorial equals 0. That is to say, the limit of Rnx equals 0 when n tends to positive infinity. Please study example 2. Please try to find the Maclaurin series for cosine x and proof that it presents cosine x for all x. Since fx equals cosine x, f0 equals 1. Since f prime x equals minus sine x, f prime 0 equals 0. Similarly, since the fourth derivative of fx is cosine x, its value at 0 is 1. Thus, the Maclaurin series is the following expression. Then, proof that for all x, we have the limit of Rnx equals 0, since the absolute value of the n plus 1th derivative of f equals the absolute value of sine x or cosine x. We have the absolute value of Rnx is less than or equal to the absolute value of x to the power n plus 1 over n plus 1 factorial. For all x, the limit of x to the power n over n factorial equals 0. That is to say, the limit of Rnx equals 0, where n tends to positive infinity. Please look at example 3. Thinking about the question, how to get cosine x through sine x. We have proved that sine x equals the expression in red font. Since cosine x equals the first derivative of sine x, we can easily get that cosine x equals the following expression by derivative computation in black. Please look at example 4. Try to find the Maclaurin series for fx equals cosine x into different ways and show that it presents cosine x for all x. We can show the question in two ways. Method 1. Since fx equals cosine x, f0 equals 1. Since f prime x equals sine x, f prime 0 equals 0. Similarly, since the fourth derivative of fx is cosine x, its value at 0 is 1. Thus, the Maclaurin series is the following expression in red font. We can show the question in method 2. Since the exponential function of x equals this series, cosine x equals 1 over half times exponential function of x plus exponential function of minus x. By calculation, we can get that cosine is x equals the series in red font. Next, we look at example 5. Suppose f(x) equals arctangent x. Please express it by power series for x. Since the first derivative of arctangent x equals 1 over 1 plus x to the power 2, and pay attention to the fact 1 over 1 plus x to the power 2 equals 1 minus x to the power 2 plus x to the power 4 plus minus 1 to the power n times x to the power double n. We have arctangent x equals the integral of 1 over 1 plus t to the power 2 with respect to t from 0 to x equals Let's continue to study example 6. Suppose f(x) equals ln 1 plus x. Please express it by power series for x. Since the first derivative of ln x plus 1 equals 1 over 1 plus x, and 1 over 1 plus x equals 1 minus x plus x to the power 2 plus minus 1 to the power n times x to the power n when x is between minus 1 and positive 1. We have ln 1 plus x equals the integral of 1 over 1 plus t equals the last expression when x is in the half open and half closed interval from minus 1 to positive 1. Please look at example 7. Since ln 1 plus x equals this series and ln 1 plus 1 equals ln 2, we have ln 2 equals 1 minus 1 over 2 plus 1 over 3 plus minus 1 to the power n minus 1 times 1 over n. Since arctangent x equals this series and arctangent 1 equals pi over 4, we have pi over 4 equals 1 minus 1 over 3 plus 1 over 5 plus minus 1 double n plus 1. Please look at example 7. Suppose f(x) equals x minus 1 over 4 minus x. Please express it by power series in x minus 1 and find the nth order derivative of x minus 1 over 3 to the power n when the absolute value of x minus 1 is less than 3. At point 1 over n factorial equals 1 over 3 to the power n. So, the nth derivative of f at point 1 equals n factorial over 3 to the power n. Now, please think about the question. If f(x) equals 1 over 4 times ln 1 plus x over 1 minus x plus half arctangent x, find the power series for x. By derivative computation, we have the prime of f equals x to the power 4 over 1 minus x to the power 4. By NL formula, we have f(x) minus f0 equals the integral of f prime x equals the summation of x to the power 4n plus 1 over 4n plus 1. By f0 equals 0, we have f(x) equals the summation of x to the power 4n plus 1 over 4n plus 1 when x is between -1 and +1, and n from 1 to the positive infinity. Finally, we summarize this class. Suppose that f satisfies this expression for all x in some interval around the given point A, then the corresponding coefficient Cn equals the nth derivative of f at point A over n factorial. Let f be a function whose n plus 1th derivative exists for each x in an open interval I continue A. Then, for each x in I, f(x) equals the expression in right form, where the remainder of error Rnx is given by the formula Rnx equals the n plus 1th derivative of f at point C times x minus a to the power n plus 1 over n plus 1 factorial, and pay attention to the fact C is some point between x and a. Thank you for your listening. See you next time.